So welcome to part B. Now, before we start, I'll say this part B has a little bit of the thing, but hopefully it's a very, very important part because this, again, brings us another very important notion in topology, which is compactness. Yeah. But it has a lot of mumbo jumbo stuff, so it's very important for you to to wrap your head around this. So yeah, so the first notion we need is that of open cover for our purposes. So giving a topological space, a collection of open sets. You know what open sets means is that the collection is a sub-collection of the topology. Is said to form an open cover if when you take the union of all the members of the collection, you recover X. So you get X back, okay? Now, the indexing set I, this indexing set, in principle, can be anything, really. It can be infinite. It can even be, uncountable, okay? So it doesn't really, there's no restriction on what this indexing set can be. Obviously, as you will see in the next few slides, especially in the case of compactness, we require something a little bit more, less wild, okay? And another thing I want to say is that we could have started the definition in a more abstract fashion by defining the notion of cover as being a subcollection of the power set, okay? In other words, C to be contained in the power set. The power set, which is the set of all subsets of X. But we don't want to do that because what matters to us is really the open covers. That's what we are interested in. Okay. So that's what a cover is. A cover is essentially a collection of a sub-collection of the topology that when you take their union, you recover the space X, okay? Well, you can think about where, for example, this is just a thing just to see if your brain, to try to connect with the stuff that you learned before, think about bases, for example. Isn't bases a natural place where you could get an open cover, for example? Okay. Yeah, just food for thought for the time being. And then you have the notion of a subcover, and this is also, for you guys, this is also like a very obvious. So given a cover, a subcollection of that cover that we call C or calligraph C tilde, indexed by a set J, which is a subset of the index I, is a subcover if it's also a cover, okay? So in other words, this is a subcover if obviously you take the union of all its members, you recover X, okay? And very important, you will see this in a minute why this is important. In principle, a subcover can be, obviously it can be infinite, but it can also be finite, okay? And you will see this is exactly what we want for compactness, that the subcover is finite. Okay. Have I made any typo somewhere? I see Amir. How come C would not simply be C? I claim you will see some examples in practice how this thing works. At the moment, it's very abstract. Okay, so for the time being is so you have a cover C, you have a sub collection of it, and then if that sub collection happens to be a cover also, then it's a subcover. Obviously, this C itself is a subcover trivially, right? It's also a subcover of itself, right? Because it's a subset of itself. So. But that's not what we want. In practice, what you want is another sub-collection, a sub-collection, a proper sub-collection of this. That's what you want. I hope that clarified your thing, Amir. You still confused? Okay. All good? Okay. Now, here's a challenge. I hope I didn't make a mistake. Obviously, I had like 1 hour or 2 hours or something, over 2 hours to do this. But hopefully, I didn't make any mistake. It's a good thing. If I made any mistake for you guys to correct me, that's a good thing. So here's the thing. Here's a challenge for you. So the first one is let X be this open interval 0, 1, equipped with obviously the standard topology. At some point, I will stop mentioning this because it becomes obvious that all this when we are talking about these intervals and these things, or even a subset of Rn, we mean the thing with the standard topology. So at some point, I will stop saying this because it becomes like it's already obvious. Okay, but for the time being, just to remind as a reminder. So we have this open interval 0, 1. The question is if this collection here, made of these open intervals, like the interval 0, 1, the interval 0, 1, 1/2, 1/2, 1, whether these are open covers of this interval. Okay, you figure it out. If you take the union of all of them, if you recover this, then well, okay. And first of all, are they open sets for the topology? Well, this is something that you should figure it out first. Okay. And the second example now is this semi-open interval. So this thing. I mean, this is where you need to know exactly. You need to do your homework on these notions of these open interval stuff. What obviously the difference between this and this. Okay, this I'm pretty sure you already know this. So I won't even dare to insult you going through what the difference between this interval and this. Okay, so again, here's some construction of some open intervals defined like this. So Cn equals this open interval that goes from 1 over n to 1 for all n. Okay, for all. So here I'm assuming obviously 0 is not a natural number. Okay, so we will argue this at another point. So I'm starting from 1, 2, 3, 4, and so on. Yeah. So for example, C1 is equals to the interval 0. C1 equals to the interval 1, 1. C2 is equals to the interval 1/2, 1, and so on. You get the picture. So the question is, if you get this collection of these open sets, whether they provide you a cover for X for this interval, and so on. So the same thing here. Okay. So this is a challenge for you. I hope I didn't make any typo or anything, but that's a good thing. If you can find one, or you can find some, and correct me, that's fine. And another thing I want you to do. Obviously, I'm asking the question whether these are covers. So the question also is, can you find at least a subcover of the ones that are open covers? There might be all of them. There might be open covers. Well, you'll figure it out. And those that are, I want to challenge you to try to find a subcover for them. And also, are there any finite subcover? Obviously, this one here, if you figure out if this is an open cover, then obviously this is this has a finite subcover somewhere, right? So this is already very easy. Okay, so now the very important notion of compact spaces. So a compact space is nothing more than a space that has this property of every open cover has a finite subcover. Okay, so in a compact space, if you give me any open cover, I am guaranteed to find a subcover that's finite. This is great, right? This means that we can take X as a union of finite as a finite union, right? This is very easy to this makes it very clean, right? So for some K, we will always have we can recover X we can cover X finitely. This is great, Dealing with the finite stuff is better than dealing with something that's infinite, even if it's countable, let alone if it's uncountable. Okay, so this is what compact spaces give us. Okay, and now here's a challenge for you. Well, I hope you can see this. If I mean, by like by definition, like it's obvious. If X is finite, then whatever your choice of topology on you build on X, that topology is compact. Okay, I leave this as a thing for you to verify this is true. Likewise, if X is any set, whether it's finite or infinite, and equipped with the indiscrete topology, indiscrete topology meaning that the topology is made of the empty set and the X itself, then this is obviously compact also, right? You can see this. So now the trickiest one is this one. Suppose that X is infinite. Okay, X is infinite and equipped with the indiscrete topology. By that, we mean that the topology, we take it to be the entire power set. So all the subsets of X. The question is this a compact? Is this space compact? Is this topology compact? Who thinks it's a compact? Are you sure? Who agrees with the thing? Okay, so Barry disagree. This is a good thing. Anyone else thinks this the discrete topology is compact? Okay, so we have two people saying no. Okay. Yes, so it's not compact. It cannot be compact. I hope you can see this. For those of you who are still a bit of doubt to see why this is not the case, I will leave this as this is an extra challenge for you to try to see really that this cannot be compact. Okay. Okay, so another important notion is that of compact subsets. So, I mean, in the book, you might have a different definition of it, but this is the way I define it here. So, given a space, a subset A of X is compact if the induced subspace topology of A is compact. Okay? And here's a question that I want you to scratch your head. You don't have to answer now here, but the question is, does a proper subset A of X being compact necessarily means that the parent topological space is also compact? Okay, so I want you to think about it, whether a subset of X, a proper subset, whether when it's compact, it necessarily means that the parent space is compact. I hope you can see this, the answer for this. Okay, and here's another, here's a proposition. If X is compact, then any closed subset of A is also compact. Okay, and as a reminder, the thing in the first, what closed subset means is it means that the complement of it is open, right? You remember, topology 101 in the first session or so. Yeah, so this is very interesting. Not least, you have to note that in general, compactness does not imply close. So just because something is compact doesn't imply is thing. However, very interestingly, if X is a Hausdorff and the subset A is compact, then A is closed. Okay, so this is already hinting you how interesting Hausdorff spaces are, which is already giving you the sense of why we want to work with Hausdorff spaces, because they have all these nice properties. Another very interesting thing about Hausdorff spaces is that if say you have two spaces X and Y that are compact and Hausdorff, then automatically any bijective to check whether the map is invertible or not. If it's continuous, and bijective, and if these two spaces are compact, then it means that F is a homeomorphism. So this again hints you a very nice property of Hausdorffness. Okay. So compactness is then I hope you can see this again, is as you're already guessing, compactness is an invariant, is a topological invariant. So therefore you can use compactness to assess again whether two topological spaces are homeomorphic or not. If they are not homeomorphic, then they cannot be both compact. So if one is compact, the other one is not compact, then they cannot be homeomorphic. Okay. So here's a thing. First of all, let me check pause here and think I'm still with you. Am I still around? It's weird. The thing sometimes it's some like a crowdcast. Sometimes the chat gets like that's why we miss our friend Soham, because he would spot everything. Can someone type on Discord the thing, because I cannot. It's like oh, maybe yes. Sorry for that. Okay, so I see someone, Bob, saying yes. So I assume I'm still with you, right? Okay, good. Yeah, sorry for that. Thank you. Okay, so I was going. So the challenge anyway. So here's another challenge. So given two topological spaces, the question, two compact spaces, X and Y, the question is whether their product is also compact. I think some of you already, you have gone through several topological invariants so far, and you have seen that their product is always also the same, okay? So, well, I'll still ask it. It's good, nevertheless, even if you have the intuition that it is, it's good for you to try to actually prove it, okay? So, yeah. So that's a challenge there for you, whether the product of two compact spaces is also compact, okay? And then which of the following spaces are compact? Yeah, okay. So I basically just copied the previous thing of part connectedness stuff challenges to see, but nevertheless, check which of them. If they are compact, it means that obviously all of them, they must their covers have finite subcover. Okay, so the question is which of these spaces are compact. I'll leave this as an exercise. Again, I strongly advise you that try to go through this yourself. To try hard to before you look at the textbook materials or other people's solutions and these things. This is the only way that you can internalize and actually get a veil off for you to be able to see what's really going on by yourself. Okay. So here's a small thing of why compactness matters. Okay, so in module 2, you will learn about something called compact Lie groups. So obviously, the compact part of it comes from the fact that the topological structure of the Lie group is a compact compact space. So the underlying topological space is compact. So you really need to think. And here are some examples, very important. Obviously, the unitary group and the special unitary group. Now, some of you will be surprised about this because so far you have encountered these objects from a pure algebraic point of view. Now you must be wondering, how come these are like, well, there are topological spaces. The reason they are, this is something that we will do on the thing on module 2. You will learn, you will know exactly why they happen to be also topological manifolds. Okay, so the unitary group and the special unitary group, you're already starting to see, like, when people tell you that, to learn, to do quantum computing and this thing, all you need is linear algebra, blah, blah, blah. You're already starting to see that this is not true, because these things, that are very important in quantum computation, they don't just carry the algebraic structure, they carry other very rich structure that, at a higher level, like at a professional, at advanced level, research level, for instance, you need to be aware of. Okay, so yeah, the orthogonal group is another one, the special orthogonal group, blah, blah, blah. But these are all things that we will come across in the technical module 2. Okay. And just to give you a flavor, there's this paper, I forgot to put the authors. It's a book paper called Lie Theory for Quantum Control. Here's an abstract I left you for you to just try to gauge the application of these things into, say, for example, quantum computing, for instance. And there's this company, actually, I don't mean to advertise for them and these things. We have no relationship with them, but they're called Q Control. They are a quantum control engineering company in this. And if you want to work for companies like this, especially in the high technical roles, you better get your Lie stuff, especially compact Lie group stuff under your sleeve. Okay. And here's a book, actually, that should, for those of you who want to adventure into these things, you can, or maybe you should wait until you go through Lie theory stuff. But here's a group called, a book, Introduction to Control and Quantum Control and Dynamics. If you want to see how these things are applied. And obviously, the physicist guys, if you pick any thing on standard model, on particle physics and these things, Lie groups are all over this place, And here's a quote. Hopefully, this will help you build. I challenge you to try to see what the meaning of this quote. So this is one of the greatest mathematicians of 20th century, Hermann Weyl. He said, if a city is compact, at least he's quoted saying this, huh? I hope it's true. If a city is compact, it can be guarded by a finite number of arbitrarily short-sighted policemen. Well, nowadays you can say policemen and policewomen, okay? So to be more inclusive. Okay, so that's it of today. Again, just to remind you that the slides will be uploaded on GitHub. You can rewatch this on YouTube, especially if you joined late or you still have doubts. I will actually split these the thing in two parts, part A, part B, so you can focus on the part that you are most interested in or you are struggling most with. And if you haven't joined, those of you watching on YouTube or watching now, if you haven't joined Discord, I really encourage you to join Discord. And actually, well done to George and Amir for organizing for the study groups. Okay, so someone, can you go back to the slide with the abstract? Yeah, sure. Yeah. So this is just, actually the abstract is bigger than this. I just took some parts for you to see on the thing, just for you to see, because I wanted to emphasize why compact Lie groups are important, okay? So yeah, you will have this slide anyway. So you can, on the thing, you can read it and search for this paper. It's called Lie Theory for Quantum Control. You will see this. Okay, so now time for the thing, for the poll. Let's see, but you still want to see the abstract screen. Yeah, that's very very interesting thing. to ask the guys working on the thing on quantum, on the quantum stuff. Okay, so let me pull the poll. I mean, a lot of progress I've made in that in early stages of the thing. You know, these are not close to useless because people can play, do toy stuff with them. But yeah, let's see, where did I put my poll? Okay, yeah, it's invisible. So okay, so this time at this point I've stopped asking whether you want 1 week or 2 weeks. It seems like most of you want like a 2 weeks gap. So in this case I put 3 weeks gap as an alternative in case, because this is really the last chance for you to wrap your head around. So if you are struggling, you need more time to catch up, and with the stuff that we've been covering before we get to the manifold section, maybe 3 weeks is ideal for you. But yeah, so let's leave it few 1 minute or two. We're still on the thing on the hour anyway. We're still like 5 minutes. Okay, so I'll leave it to run few to see if more people. So far, it's very close actually. 60% wants October the 1st. 40% want September the 24th. So does it? Okay, so more people want September. Okay. Does anyone else want to vote? Or anyone want me? I can pull some of you if you want to make an argument for Friday, October the 1st to the rest. I can pull you in. You can say, you can convince the rest, or you can type on the chat. Maybe people will change their mind and give you. Okay, so it's like oscillating. Now we have like 57% versus 57% for September the 24th and 42% for October. Now we have like even 50-50. So what should we do? I might have to pick some of you on the audience to break the tie to see who wants the thing. I mean, all of you are all regulars, so I'm really happy to take whichever day you think. But it's really important for me. It's not like rushing to get over the crash course is less important than actually you guys being able to pick up these things. So we are not really running against time. So if you need more time in order to wrap your head around the stuff that has been covered today, but also the previous session, maybe October the 1st is best, because if you struggle with the thing, the manifold section will be even more, much more harder for you. Okay, so I mean, it's very intuitive, all this notion of manifoldness and these things. But then it's like because we are working in abstract, but at the same time, bringing in concrete stuff that you already know from calculus and these things, like differentiability and these things. It's really important that you don't have any gap in the fundamentals. Okay, so now we have 71% want October the 1st. Shall we settle for that? I need a few people to say yes on the chat. Fine. Okay. So our friend Amir is okay. Yeah. So 71% want Friday, October the 1st. So shall we settle for that? Okay, done. So the next session will be Friday, October the 1st. So I really recommend you guys to organize study groups and these things and go through these exercises and these things, to get yourself around these the stuff, because the manifold section, which is the most interesting part, will be in a way, for those of you who did calculus and these things, some of the stuff will be a kind of very intuitive for you. It's just some of the technicality, the abstract stuff is will be like new to you. These things, but yeah. But it's very important for you to get all these concepts that we've been working on, on the topological concepts, because at the end of the day, manifolds are topological spaces, right? The only thing we are adding extra structure to the topology, so we are moving slightly into the realms of other subjects like calculus, for instance. Okay, good. So that's it then. Does anyone have any other question? If not, we end it here. Obviously, we can always discuss on Discord and these things. That's why we created Discord, is for for people to be able to interact with each other. Okay, good. Okay, in that case, thank you so much, everyone. It's been a pleasure to be back with you all, and I hope to see you again on October October 1st. I hope I got the date right. Huh? It should be, yeah. So yeah, well, in that case, thank you so much again, and it's been fun to be with you. And yeah, we catch up in the next session, where we'll finally get into topological manifolds. Okay, the exciting stuff. Thank you. Okay, bye. Okay, thank you, George, for offering the study session again on Friday. It's really important. I encourage everyone watching now, join George on Discord, to go through this stuff. Okay, good. So have a good weekend, and we catch up in 3 weeks.